welcome back. The last time we had some fun with one variable calculus. In particular, we came up with very strange examples of smooth functions, which aren't quite relevant to the rest of this course, but nonetheless it's a fun lecture, so to say. Then we moved back rather to differential calculus, starting with one variable, but eventually to more than one variable. We recalled that, for example, sine inverse of x, if it is assumed to be differentiable, has a nice formula for the derivative, and this is true even for multivariable functions. In fact, we agreed that if f dash, so rather if f inverse, let me write this down. So if f inverse is differentiable, then f dash at the point f inverse of x is not 0. But the question is, when is f inverse differentiable? That's the real question, right? So one silly answer to this, one conjectural answer to this could be, if f dash of a is not 0, then is f invertible and f inverse differentiable. Right. Now this, as written, the answer is obviously no, right? I mean, for example, if you take sine x from r to minus 1, 1, right? Obviously, sine of, let's say, sine x, the derivative at x equals 0 is cos of 0, which is equal to 1, it's not 0. This doesn't mean that sine is invertible, right? Obviously, just because the derivative is not 0 at a point doesn't mean f is invertible everywhere, right? But even so, I mean, this example you might object is a bit unfair, but nonetheless, even in this example, there is still something you can say, right? What you can say is, instead of restricting your domain to all of R, if you restrict it to minus pi by 2 comma pi by 2 and your range to minus 1 comma 1, yeah, namely, so sine of 0 is 0, right? So this is minus pi by 2, this is pi by 2, this is minus 1 and this is 1. So if you restrict your domain and range a bit, then sine is indeed invertible. The claim is also that sine inverse is differentiable, but it's not obvious, right? So this example, regardless of how silly it sounds, tells us that this question must be modified. Modified to what? The question then is, if f, let's say from R to R, not necessarily R to R, but anyway, is assumed to be C1, and if f dash of a is not 0, then is f locally invertible near f of a, and is the local inverse differentiable at f of a, or differentiable. Okay. What does this mean? What does the word local mean? Local simply means, as the English word suggests, right? Nearby, right? Locally, near that point of interest. So in other words, if f is assumed to be C1 and if f dash is not 0, is there some neighborhood containing A, some, let's call it A minus delta and A plus delta, such that if you take the image, this is f of A plus some epsilon and f of A minus epsilon. The claim is, the question is does f inverse exist if we restrict our domain and range a bit to appropriately chosen neighborhoods of A as well as f of A? Does f inverse exist, and is f inverse differentiable? This is a perfectly reasonable question. At least our previous example of sine inverse does not exclude this possibility. In fact, the answer to this question is a resounding yes. Okay. So this question can be answered in the affirmative, and let's actually prove this, right? So how does one prove this? If f dash is not 0, right? Now then what can we say? F is C1, right? I mean, we don't really need this, but might as well assume this just to make our lives a little easier. F dash of x is not 0 for all x in a neighborhood of A. By continuity of the derivative, right? We've assumed it's C1, so if f dash of A is not 0, f dash of x continues to be non-zero in a region around A, right? In fact, if it is not 0, f dash of x has a sign, meaning it's either positive or negative. It can never change the sign. Because if it changes the sign, it must have become 0 somewhere, and that's not allowed, right? Now if f dash of 0 is positive, what does that mean? The function is monotonic. So f is either strictly increasing on this neighborhood or strictly decreasing. So it is strictly monotonic on this neighborhood, right? So in other words, if you take f of A minus delta and f of A plus delta, let's take the interval, let's say without loss of generality, it's strictly increasing. It can be strictly decreasing too, there's nothing wrong, but without loss of generality, let's say, because the same argument applies. So this, you have a map f from here to here, and this map is onto. Why is it onto? Because f of A minus delta and f of A plus delta, by the intermediate value theorem, all the values in between f of A minus delta and f of A plus delta are assumed by the intermediate value theorem. So it's onto. It's also 1 to 1. Why is it 1 to 1? It's strictly monotonic. So it's 1 to 1, meaning it is invertible, right? In fact, the inverse is also continuous. Why is the inverse continuous again? What does it mean to be continuous? So here I'd like to introduce a small concept. I mean, if you've done metric spaces, you would have seen this. But if you haven't, let me just tell you nonetheless. So suppose you have a function from, in fact, Rn to Rm, some subset of Rn if you wish to Rm. F is continuous on S if and only if the inverse image of any open subset in Rm is open. By open, I mean the inverse image equals an open set in Rn intersect S. So you can talk about continuity by using just open sets without any deltas or epsilons. This is an exercise. I'll leave this as an exercise to you. But what is the basic idea behind the proof of such a statement? If f is continuous, well, what is our classical definition of continuity? It means it's continuous at every point. In particular, f of x can be made epsilon close to a provided x is delta f of a provided f of x is delta close to a, right? What does that, why would that imply f inverse of an open set is open? What is f inverse of an open set? It's the collection of all x such that f of x lies within an open set. Suppose we take this open set and we take a point in it. What is the property of an open set? That if you take any point, there is some small open ball around that point that is completely contained within this set. So suppose you take a point in this open set, let's call it f of a. So there's an entire ball around this, a ball of radius say epsilon around this around f of a, which is completely contained in this set, right? Now the pre-image of it is the collection of all x, so that f of x is epsilon close to f of a. This is certainly achieved when x is delta close to a, right? So this doesn't immediately prove what I just said, but this is the basic idea. Okay. It will require a little bit of work to do this exercise, but nonetheless I encourage you to do it anyway. Coming back to this, f inverse is continuous. Why? The easiest way of saying, you can do it by scratch, by the way. You can, what does f inverse being continuous mean, right? Well, if you want to do it using epsilons and deltas, you would want to say that f inverse of x must be close to f inverse, let's say, must be, say, close to b whenever x is close to, let's say, f inverse of b, x minus b is less than delta. This is what you would want, right? You can of course do this from this also. It's not too difficult to prove this. Why? Because f is monotonic, right? So using that, you can actually prove that whenever x and b are very close, this is the case. But a slightly simpler way of saying this is f inverse of an open subset in here, which is f of open, is this open or not? And this part is true. The reason is, again, by the intermediate value theorem and monotonicity. So if you take any open interval, where does it go under f? It goes precisely to an open interval, thanks to exactly the same reasoning that led to this. Okay. So f inverse is indeed continuous. It exists and it's continuous. The next order of business is to show that f inverse is actually differentiable, right? So far, okay, what we have done, what are we trying to do again? What we are trying to do is, we are told that f dash of a is not 0, so we are trying to prove it's locally invertible. So we have come up successfully with an open set around a and an open set around f of a, and such that this is 1 to 1 on 2. So the inverse exists. We have argued that the inverse is continuous. Given this, why is the inverse differentiable? right? What does differentiability mean here? So differentiability would mean f inverse of f of b plus h minus f inverse of f of b divided by h must exist, right? Okay, so suppose, so what is f inverse of f of b? So this is f inverse of f of b plus h minus b divided by h. Yeah, right. So if you call this k, right? So f inverse of f of b plus h is b plus k, which means f of b plus h is f of b plus k. Yeah? Right. So what is this? This is limit, before we take the limit, this is k divided by f of b plus k minus f of b. Now the key point here is that as h goes to 0, k goes to 0 as well, right? Why is that so? Why is that so? The simplest way to see this, yeah, so why is that so? The point is, we've already proven that f inverse is a continuous function. So as h goes to 0, this goes to f of b, and therefore f inverse of this by continuity would go to b, which means k goes to 0. This is from the continuity of f inverse. So this is the same as the limit as k goes to 0 of this, which is 1 by f dash of b. Yeah. So not only have we proven f inverse is differentiable, we've also found a formula for this, and this formula will tell us that f inverse is C1. In other words, the derivative of f inverse is also continuous. Yeah. So in other words, from the assumption, what is the point, what are we trying to say here? If f is C1 and if f dash is not 0, it is locally invertible, the local inverse is differentiable, and the local inverse is not just differentiable, it is C1. What does this mean? If f dash of a is non-zero, there is a neighborhood around a and a neighborhood around f of a, so that when you restrict f, that is, you restrict the domain and range of f to small open sets, this beast, this resulting restricted f is actually invertible, and the inverse is C1. This is sort of an if and only if criterion in some sense, right? Because if f inverse is indeed, f inverse is indeed differentiable, we have already agreed that f dash of a must be non-zero. What we have shown now is the converse, that if f dash of a is non-zero, then f inverse locally exists and is differentiable. In fact, it's C1 if the original one is C1, right? Again, what's the proof of it? I mean, what we did was to first show that the f takes an open interval around a to an open interval around f of a in a one-to-one onto manner. The one-to-one aspect followed from monotonicity. So did the onto aspect, but it involved one important theorem, namely the intermediate value theorem. Once we did that, we proved that f inverse is continuous, or rather, I sort of waved my hands a bit intentionally, because I would actually want you to prove this on your own. Yeah, I want you to prove this. I mean, either you prove this, firstly do this exercise, but also do this from scratch, right? It's not as difficult as it looks. Basically, f is monotonic, right? So f inverse of x being epsilon close to f inverse of b would mean, for instance, if f is increasing, f inverse of x is less than epsilon plus f inverse of b, larger than epsilon minus f inverse, minus epsilon plus f inverse of b. Now, you can apply f on both sides and the inequality will still be preserved if f is increasing, right? So then you can conclude that x is less than f of f inverse of b plus epsilon, and x is larger than f of f inverse of b minus epsilon. That will enable you to conclude this by using the continuity of f itself, basically. Okay? Roughly speaking, not exactly, but roughly speaking, this is the idea behind how to do this directly. Okay? It's a nice exercise in one variable real analysis, so I urge you to do it nonetheless. Okay? The reason I'm not making too fine a point about this is because we will do this anyway in multivariable calculus in a moment, but I just wanted to give you motivation for what is to come. So what did we do? We proved that f is locally invertible. We proved f inverse was continuous. That required most of the work. Given this, proving that f inverse is actually differentiable and the derivative is also continuous is actually not so difficult. It's almost like changing the variables a little bit. Okay? It's not rocket science really. Okay? The difficulty lies in proving that f is locally invertible and that the inverse is continuous. Okay? And even within proving f is locally invertible, the real difficulty was in proving that it is onto an open set. Here we use the intermediate value theorem, but such a strategy will spectacularly fail in more than one dimension because we don't have the intermediate value theorem there. Yeah? Okay, so this theorem, the answer to this is yes, as I said. This theorem is called the inverse function theorem in one variable calculus. Okay. This is called the inverse function theorem because it tells you when the inverse exists and is differentiable, right? So the next order of business would be to generalize it to more than one variable. Okay. But before that, it's very important that if f is not C1, we can run into problems. For example, if f of x equals x plus 2x squared sine 1 by x, when x is not 0, and 0 when x is 0. Yeah? Now this function is certainly continuous. As x goes to 0, this goes to 0. Why does this go to 0? The reason is whatever sine 1 by x is, mod of that is less than 1. So by the squeeze rule, since this goes to 0 and this is less than 1, mod of it, this goes to 0. So f is continuous. Is f differentiable? Well, let's see. F of h minus f of 0 divided by h, which is limit as h goes to 0, 1 plus 2h sine 1 by h. This is 1. Why? Because again, by the same squeeze rule kind of reasoning, this goes to 0 because sine of 1 by h, whatever it is, it's bounded between minus 1 and 1. So when you multiply it by h, this goes to 0. So it is differentiable no less, no doubt, and the derivative is 1. Is the derivative continuous, right? And the answer to that is, of course, it's not. I mean, it's not of course. Let's actually compute the derivative. So it's plus 4x sine 1 by x minus 2x squared by x squared cos of 1 by x when x is not 0. Is this continuous? That is, as x approaches 0, what happens? This becomes 1, this goes to 0. This limit does not exist as x approaches 0. Okay, cos of 1 by x keeps oscillating. For example, I invite you to prove this rigorously by choosing a sequence of x's. Right? For example, if I choose 1 by x to be such that cos of x is 0, that's great. But I can also choose 1 by x so that cos of x is 1. Right? So cos of 1 by x, cos is 1 at infinitely many points. You take 1 by those points to be your x, then cos of 1 by x will be 1 at infinitely many points, and those points approach 0. Right? So that's the trouble here. Okay? So this limit doesn't exist. So in other words, f is not C1. And what do we mean by saying it runs into problems? It is not locally invertible near 0. That's the trouble here. It's not locally invertible near 0. Meaning, regardless of how small a neighborhood you choose around 0, this, for example, will not be 1-to-1 on such a neighborhood. Okay. Why would it not be 1-to-1? Well, I invite you to try to prove this on your own. It's not trivial, right? But you can take this on faith that this example unfortunately shows that being C1 is an extremely important requirement. Okay. Right. So the theorem that we are after, I'll state it. This is the famous inverse function theorem in multivariable calculus. Let f be a CR where R is between 1 and it can be infinity to function on an open set U. If dfa is invertible, then there is a neighborhood V of A such that f of V is open in Rn, f from V to f of V is 1-to-1, and f inverse from f of V to V is CR. Okay? So the inverse function theorem is a direct generalization of its one variable counterpart. If you have a CR function on an open set U, yeah, I mean obviously we always demand that our sets be open because we've agreed that differentiability makes most sense on open sets. So suppose you have a CR function where R is at least 1, it can be infinity too. If the derivative at a point is invertible, then the function is locally invertible and the local inverse is also CR. In particular, if you have a smooth function and if the derivative at a point is invertible, if the derivative matrix at a point is an invertible matrix, then the function is locally invertible and the local inverse is also smooth. Okay. Sometimes this is stated in a more fancy way. optional if you don't want to use this fancy terminology. This is said as F is a local CR diffeomorphism. This fancy name is simply saying the following: a CR diffeomorphism is simply a CR function which is invertible, and the inverse is also CR. That's all. Okay. Local CR diffeomorphism means precisely what this is saying, that there's a neighborhood of the point of interest such that the image of the neighborhood is also an open set. Why do we want it to be an open set? Because we want to talk about differentiability of the inverse, which only makes sense on open sets. Anyway, so you have a neighborhood of the point A such that the image of that neighborhood is a neighborhood of f of A. It's an open set. F is 1 to 1, and F inverse which exists because F is 1 to 1 is also CR. It is as well behaved as the original one. So in other words, if df at a point is invertible, F is a local CR diffeomorphism. This is the statement of the inverse function theorem. So we will stop at this point and we will continue with the inverse function theorem in the next class. So thank you for joining.